Hello, calculus fans! Alright, so let's start with this function, f of x equals 2x cubed plus 3x squared minus 36x. And we're going to answer a bunch of questions about it. So first, we're going to find the intervals on which it's increasing or decreasing. We're going to find the local extrema. And we'll find the intervals of concavity and whatever inflection points there are. Alright, so we need to take a couple of derivatives. And these derivatives are not going to be hard because we're just dealing with a polynomial function. So the first derivative is 6x squared plus 6x minus 36. And it'll be useful to have this fully factored. So we start by pulling out a 6. And then what's left over, the x squared plus x minus 6, can also be factored without much trouble. And so we end up with 6 times x plus 3 times x minus 2. All right, now we're going to need to take the second derivative. So the second derivative is 12x plus 6, and also it'll be useful to have that fully factored as well. So we pull the 6 out, and we're left with 6 times 2x plus 1. So what we'll do now is create sign charts for both f prime of x and f double prime of x. Well, let's do the sign chart for f prime of x first. Now we should be able to see from this first derivative that there are two critical numbers, x equals negative 3 and x equals 2. So let's set up the sign chart before we fill anything in, just as we had done before. Because we have negative 3 and 2 as our critical numbers, then we set up our intervals with those as the breakpoints. So we're going from negative infinity to negative 3, then negative 3 to 2, then 2 to infinity. And now, just as we had done before, we're going to figure out pluses and minuses for the individual pieces. So what we'll do is plug in some test values and then see what the sign of each piece is. Okay, so here I'm showing the sign chart that's filled in. You should pick some test values, like for the first interval you might pick negative 4, and then you should be able to see that both of these are going to be negative. That means the end result is going to be positive over here. So we should be able to see that the positive that we get here means that the function is increasing. So double check the values in the table, make sure they agree with what you have. And now that we have the table, we can talk about increasing and decreasing. So this tells us that the function is increasing on the interval from minus infinity to negative 3, and also from 2 to infinity. And then it's decreasing on the interval from negative 3 to 2. Okay, now we want to classify these critical numbers using the first derivative test and the second derivative test, just to show how they both work. And we're going to see if any of them are local extrema. All right, let's classify x equals negative 3. Okay, so we're going to use the first derivative test. We notice that before x equals negative 3, the function is increasing, and then after negative 3, it's decreasing. The first derivative test then tells us that we've got a local maximum. It's going up, then it's going down, so that has to be a local maximum. Now we can use the second derivative test by plugging in x equals negative 3 directly into f double prime. And what we'll get is this value here. I don't know exactly what that number is, but it doesn't really matter. What matters is that it's negative. And then the second derivative test then tells us that x equals negative 3 is a local maximum. Now let's do the same kind of classification for x equals 2. Now note that the function is decreasing before and increasing after. The first derivative test then tells us that x equals 2 is a local minimum. Now we could use the second derivative test and plug x equals 2 directly into f double prime. This time we end up with a positive number, and the second derivative test then tells us that x equals 2 is a local minimum. Positive number means it's concave up. Okay, so the next thing we'll do is create a sign chart for f double prime because we want to answer some questions about concavity and inflection points. Now we only have one point where the second derivative is equal to 0, and that's when x is equal to negative 1/2. So go back and look at the second derivative and set it equal to 0, and we'll get this. So let's do our setup for our sign chart for f double prime. Right, since we're breaking things up at negative 1/2, then our intervals are going to look like this. Now the same sort of deal, we'll just pick test points and look to see where the second derivative is positive and negative. So when we plug in those test points, then this is what we're going to get. We'll have a negative value on the first interval and a positive value on the second interval. So remember that a negative second derivative means that the curve is concave down. A positive second derivative means it's concave up. All right, so it should look like this. We have concave down from negative infinity to negative 1/2 and concave up on negative 1/2 to infinity. And then the last piece is that since the concavity changes at x equals negative 1/2, that makes it an inflection point. Okay, that's all for now.